Hello, my name is Hyungchul Park from Intelligent Wave Systems Laboratory, and I'm going to present wave localization in disordered hyperbolic lattices. For the first part, I'm going to introduce hyperbolic geometry and Anderson localization, and explain motivation for studying Anderson localization at hyperbolic lattice. And the second part, method for studying wave localization phenomenon at hyperbolic lattice will be introduced. And for the third part, localization behavior for different hyperbolic lattices will be presented. And the last part, I'm going to summarize the result and explain the future work that we plan to do. Hyperbolic plane is defined as surface with constant Gaussian curvature. Gaussian curvature at point P on surface is defined as multiplication of minimum curvature and maximum curvature of curve that pass through point P. For the Gaussian curvature to be negative, every point on surface should be saddle point, because if the curve is local minima at point P, then the curvature will be positive, and if curve is local maxima at point P, then its curvature will be negative. Thus, only saddle point can have negative Gaussian curvature, and every point on hyperbolic plane should be saddle point, making visualizing it in Euclidean space very hard. More simpler model can be constructed by embedding the structure at Minkowski space, which is called hyperboloid model. Because it is known that isometric transformation preserve Gaussian curvature of given manifold, we can construct simpler model called Poincare disk model by projecting it onto unit disk and defining appropriate metric on it to make transformation isometric. Poincare disk is often used to visualize hyperbolic geometry because it can visualize hyperbolic geometry not by embedding it in higher dimensional manifold, but on unit disk, which is two-dimensional manifold. So why are we interested in hyperbolic lattice? Before we proceed, we need to generalize the notion of Bravais lattice. We can do so by defining it as tessellation of given space with regular polygon. For Euclidean space, only three kinds of tessellation of given space is possible: honeycomb, square, honeycomb, and triangular. The class of lattice is indexed with P and Q, also known as cloth-like symbol. P denotes the number of edges of regular polygon, and Q denotes the number of polygons surrounding its vertice. For example, square Euclidean lattice is constituted with polygon with 4 edges, and each vertex is surrounded by 4 polygons, so its cloth-like symbol is 4, 4. In contrast to Euclidean space, at hyperbolic space, infinite number of tessellation of given space is possible, providing rich class of lattice to study wave behavior. Owing to rich class of lattice, unique wave behavior unseen at Euclidean lattice is reported at hyperbolic lattice. For a hyperbolic Kagome lattice, spectrally isolated flat band is reported, as can be seen in figure D and figure F. On the other hand, for Euclidean Kagome lattice, flat band is connected to other part of spectral band, as can be seen in figure C. It also has reported that by empirically defining Chern number at hyperbolic space, unique shape of Hofstadter butterfly is obtained, as can be seen at figure DEF. You can see the spectral band becomes narrower as Q is incremented from 4 to 5 to 6. The wave property we are going to see is Anderson localization, which is disorder-induced wave localization phenomenon. While perfect crystal shows behavior of perfect conductor, as disorder is increased, conductance eventually drops to 0. Anderson explained this phenomenon by introducing Anderson model, which is tight binding model with disorder given a resonating frequency of isolated lattice site. Extended state is characterized by uniformly distributed wave function, and localized state is characterized by few lattice size with large amplitude and exponential decay around it. As disorder is increased, state transitions from extended state to localized state. You can see how localized state mode profile looks at the right figure. The motivation to study Anderson localization at hyperbolic lattice is presented at next slide. Before that, let me briefly introduce scaling theory of Anderson localization. Metal is the localized phase of material, and insulator is localized phase of material. And its distinction can be made by applying scaling theory. Scaling theory is theory of how the system parameters such as conductance and mode size changes as system scale is changed. G at first figure denotes the conductance of material, and beta denotes exponent at which conductance changes on system scale. If beta is larger than 0, as system scale is increased, conductance increases, meaning it is metal. On the other hand, if beta is smaller than 0, if the system scale is increased, conductance diminishes, meaning it is insulator. You can also see that the localized to localized phase transition occurs only at 3D, and it is known that only at the transition point, mode size of eigenstate shows multifractal behavior, which means that its scaling behavior cannot be explained by power law of single-dimensional parameter. Other unconventional structure shows unique characteristic. One of the studied structure is Cayley tree geometry shown at right figure. It has been reported that Cayley tree shows distinct behavior from Euclidean lattice, in that it shows multifractal behavior even at the localized phase. Hyperbolic lattice is interesting in that it possesses geometric property of lattice and tree. It has characteristic of Euclidean lattice in that assuming infinite lattice, every point is symmetric. But it also has the characteristic of tree in that number of atoms scales exponentially as system size is increased. This is the reason why we hope to see unique localization characteristic at hyperbolic lattice. We research diffusion exponent of given system to study its localization property because it is directly related to transport characteristic of given medium. Diffusion exponent is defined as exponent the mean square distance of given mode increases by. We can measure the distance in hyperbolic geometry by using Poincaré disk model, which is given as following equation. Another problem that needs to be addressed is that because simulation is done at finite size, effect of boundary should be discarded. Boundary effect can be discarded by carefully choosing the duration of simulation. Simulation is stopped when the mode boundary energy exceeds the threshold value, and threshold value is chosen by observing mode profile, boundary energy, and diffusion exponent. You can see that at the stop time, mode is about to reach boundary, and diffusion exponent abruptly drops after stop time, which validates the choice of our stop time. So this is when there is no disorder. Mode is transferred ballistically in time. It is known that ballistic transport yields diffusion exponent of 2, which agrees with our simulation. And as the disorder is increased, it transitions to diffusive transport regime. You can see that exponent alpha is dropped to 1, and mode evolutions in a diffusive way as seen at mode profile. And as disorder is further increased, the mode eventually freezes, and the mode remains at its position. Hyperbolic lattice shows similar behavior as in Euclidean lattice when there is no disorder. Mode is ballistically transported when there is no disorder, and it yields diffusion exponent of 2. However, for a hyperbolic lattice, it is not localized even when the disorder is raised to 0.1. It just transitioned to diffusive regime, meaning exponent is dropped to 1. Resonating frequency is 1, thus disorder 0.1 means 10% disorder is introduced at resonating frequency, which is a very strong disorder. It can be seen that hyperbolic lattice shows strong immunity to localization compared to Euclidean lattice. The results are shown for different types of lattice. 4,4 lattice is Euclidean and others are hyperbolic. It can be seen that hyperbolic lattice shows strong immunity to localization in contrast to Euclidean, and this tendency increased further as P and Q increased respectively. In conclusion, this work first measured the diffusion exponent on hyperbolic lattice using Poincare disk model, and demonstrated that hyperbolic lattice is more immune to localization than Euclidean lattice. This tendency increased as connectivity is raised by incrementing P or Q. But this work is yet to show physical reason behind this phenomenon. And furthermore, measured diffusion exponent is hard to be said as characteristic of system because simulation is stopped when boundary is reached, and there is possibility that diffusion exponent would have dropped further if the system was larger. To resolve this issue, application of scaling theory on mode size should be done, and measured diffusion exponent should be associated with the scaling theory. Furthermore, we plan to analyze the structure with multifractal theory at different phases of material, which is the localized, critical, localized phase. Finally, we plan to measure transmittance and reflectance of hyperbolic lattice by defining appropriate scattering geometry on it and associated with scaling theory. So this is all I prepared for this presentation, and thank you for listening.